Alright, hello everyone, and welcome back to another design lecture, another video. Today we're going to be talking about FRC parts. So FRC First Robotics Competition, a student available robotics competition, basically just a student-led engineering venture that's practical or with practical experience involved. So today we're going to be talking about the different types of parts that we use for design. And if this seems a little bit off topic to what we covered last week, that's because last week was sort of a general overview. This week we're actually going to be talking about practical design tips and techniques, really, and the design language of robotics and of engineering in general, of practical engineering. But one of the most important things you can know as a designer is what parts you have to work with, because that will change what your design looks like. And a lot of these parts that we'll show today are actually applicable between many different practices, mostly engineering, right? But between many different fields of engineering and engineering study. So a lot of this you might want to hold on to, right? It's good information because it's practical information, which is the best information. So we'll be covering FRC parts, and while this may be like a little bit of a more boring presentation, it's going to give you a lot of useful information that you will use when you're designing. So I would highly recommend that you stick around to the end, because you're going to have a lot of good information in here. All right, so let's go to our first slide here. So parts are used to build the robot's mechanisms, and the mechanisms make up the full robot. So mechanisms are mechanical subsystems that fulfill a task, right? And that makes up the full robot, which can do many tasks because it has many mechanisms. So each type of part does different things for your designs and physical mechanisms, right? Right here we have a sort of a nonsense assembly, actually, but it sort of illustrates nicely the four main types of parts that we're going to be using when designing and building practical mechanisms, especially for student-led robotics. But first we have our raw materials, right, which are machinable and make up the main structure of the mechanisms. So this is, right, like I said, is sort of a nonsense assembly, but you can see we have raw materials here, which is going to be 2x1 aluminum and 1x1 aluminum. This is VexPro's VersaFrame, but it's aluminum stock, basically, 2" by 1" and 0.1 wall thickness, 0.1 inch wall thickness. And you can see here, right, raw materials are machinable and they make up the main structure of mechanisms. So basically that entails you can cut them, you can drill holes in them to connect them to other raw materials, and then make up the main frame members, the main structural members of your mechanisms. So yeah, remember that. And right, you can see here that these raw materials, they make up the main structure of your mechanisms here, and you've got joints between them. And then you have actuators, which create and facilitate motion, right? So an example of an actuator is a motor here, right, which creates a rotary motion, and that rotary motion can be used to do a whole lot of things, but not without moving parts, which translate motion into a usable force, right? So you have your gear, which is a moving part, and your gear, this gear, well, actually it looks like it does do something. So you have this pinion gear on this motor, which connects to this gear, which connects to this shaft, which is a shaft is another type of moving part. We typically use hex-shaped shafts, so hexagonal. And that's because they grip onto stuff good, right? Like they don't really want to rotate inside a hexagonal shaped hole because there's a lot of surface area in contact, and there's also angles. So yeah, moving part, you have a gear here, right? And that goes to this shaft, which goes, I'm assuming, to this shaft. I can't really see there. But yeah, it goes to this shaft, which they must be connected by some sort of chain, right? So you have sprockets around here and a chain around there. And I will explain in further detail all of these things I'm talking about right now in this presentation. And then that goes to another gear, which connects to another gear. And that connects to a sprocket, which connects to a chain, right? And that chain goes around a sprocket. Sprockets are just what chains go around. And that sprocket connects to this shaft, which just spins freely, it appears. And then you have another motor, and this is a gearbox, which is, it has a bunch of little versions of these gears inside of it, and they're moving like in orbits. And so they create a reduction in a very small form factor. And that connects to a chain, another gear, which appears to be floating in space. Again, like I said, sort of a nonsense assembly, but yeah. And then you have another moving part here. So moving parts translate motion into a usable force. And then you have hardware, which holds everything together. Not that complex, right? So you have your hardware, like this gusset here. Gusset's a flat piece of metal that holds stuff together. Like these brackets here, right? Like these brackets here. And then like these bolts, right? Bolts through here. And like these rivets here. So all of these basically just, make a sandwich going through a hole, and then clamp down, giving you a joint force, right? Giving you a connection. So we just talked about the part categories, but at the end of the presentation, we'll look through last year's competition robot and try to find each one of these parts on the robot. It's going to be quick. It's going to be a quick activity, but I think it's just, another way to keep this grounded in reality is to see it on an actual design. I really think that's the best way to do it. So yeah, try to think about how each component contributes to an overall design as we do this. But right now, we're just going to be looking at the different types of parts. First, we have raw materials, right? Machined into specific parts. We start with these, and they comprise structural members. So we have metal first. Really what we use is aluminum, right? Typically. So you have stock, which is like in sort of this form factor, right? It's hollow in the middle, and it's got different dimensions around. So you can have 2 by 1 inches or 1 by 1 inches are typically what we use, and that's this cross section here. And then you have thick wall versus thin wall, right? So that's thin. That's this wall length here, or wall thickness here, and that really dictates your strength, right? How likely this is to bow, but it also dictates weight, right? Keeping weight down is important. It's not the most important. It's better to have something be strong than it be super light, but sometimes you make that trade-off, and sometimes you don't need strength, so you use some sort of thin wall material. Actually, thin wall is pretty much the default. You go thick wall when you need something pretty chunky. So yeah, VersaFrame has a built-in hole pattern. It's basically just stock from Vex Pro, which is a robotics specific seller. But it has a built-in hole pattern here on the sides as well as grooves on the top here. Comes in the same size as regular stock. And then sheet metal is good for custom parts. It's not pictured here, but this is sort of made out of sheet metal. Sheet metal is just like a flat piece like this. You can bend it in different places, and you can cut holes in it. So you could make this out of sheet metal theoretically, right? You do it as one flat piece, machine that, you drill holes along here, and then you'd have it be a flat piece, and then you would bend it here 90 degrees, bend it here 90 degrees, here 90 degrees, and then you do like a weld here in order to get it to be like this. And then you have steel, which is not really used, but it's a lot heavier and not a lot stronger. So it's only really used if you need to weld stuff. And even then, like, you can weld aluminum. We actually have TIG aluminum welding capabilities, but welding aluminum is a little bit trickier, but it is possible to do. So steel is not really used unless you really need some really big strength. Even then, though, you can just get it with thicker aluminum. All right. Now we have wood. So wood planks, like 2x4s, except we don't use 2x4s. Typically, we use 1x2 wood, or some sort of 2x4 wood, actually for prototyping. So that's going to be really cheap, right? We can get it from our theater shop at school, and we can machine it really easily. So we can drill holes in it, we can cut it, and we can make it into whatever we want it to be. It's easily accessible, like I said. So we typically use it during the prototyping phase of design, like I was talking about before. You make your design, give it to mechanical, they build a prototype out of wood just to test feasibility. And then you have plywood and particle board, which is like flat wood, basically. So it can be machined really easily. And it's also relatively strong. It's good for really precise prototypes if you want to build different plates and then like interlock them together somehow. It can also be laser cut if you have that capability, as well as routed. I don't know if you can cut wood on a water jet. I don't think that would turn out too well. Now we have polycarbonate, which is basically just a lightweight machinable plastic material. It's used when you need something in a place, but you don't want any weight, and you don't really need much strength there. So it's usually used for various aesthetic or non-structural components. Right? It can be used structurally. There's not an example of it being used structurally here, but it can be. Many intakes have their side plates here made out of polycarbonate, and that's just because it can wobble a little bit, so if it gets hit, it's going to bend instead of break. But it also can be used structurally, like polycarbonate is what makes bulletproof glass eventually. Of course, it has to be very thick, but right in thick gauges, it can be quite strong. It can also be used in portions that will not be heavily stressed, right, but need a material in place, like this container wall. This is a big container on a robot, holds a bunch of balls, and they all sit in here. And if there was nothing here, the balls would all fall out the sides, as you can imagine. So there needs to be something here, but something lightweight and something that doesn't take up a lot of space. And polycarbonate does both of those, and you can also put sponsor logos on it, so that's nice. And it's also clear, as you can see. Although maybe they painted it clear, I think you can paint it other colors too. But yeah. All right, actuators. Actuators are used to move parts and assemblies, right? So they create motion. Uh, the first actuator type we have here is motors. We talked about that earlier. And motors are used to provide rotary movement, so circular movement, right? This shaft spins when you apply current, when you apply voltage to these motor tabs. And that's electrical stuff. Gosh, it freaks me out, but like, kind of got to know it. So yeah, uh, basically motors, all you need to know is there's brushed motors and there's brushless motors. Brushless motors are expensive and very strong, um, and brushed motors are cheap and a little bit weaker, and also a little bit jankier, but they work just as well. So yeah, they're quite effective. Brushless motors are also more controllable. You can get a little bit more controllable actuation out of them. So some notable brushed motors are 775 Pros and Sims, and some notable brushless motors are Falcon 500s, Neos, and Neo 550s. Yeah. And then you have servos, right, which are basically just motors with integrated gearboxes, like little tiny motors, and they just get a tiny little, like highly controllable range of motion. So this little thing would spin, and you'd tie something here, and it would pull it or push it, right, depending on where you tie it and where you spin it. And then you have gearboxes, which is used to control the movement of motors. So you have basically a reduction, which makes your shaft spin slower than your motor, but it also spins stronger than your motor, right? Spins with more force, with more torque. So, right, you can see here that there's a gearbox. It's a planetary gearbox, like I talked about. So motor input goes in, gears reduce it. So, like, if it were a 2-to-1 reduction, you would have 2 rotations in for 1 rotation out, and you would have twice as much force coming out for out of your motor shaft. So you'll be able to theoretically, like if you were attached this to an arm with a weight on the end, you'd be able to lift twice as much weight with a 2-to-1 reduction. That's an oversimplification, but it's basically how it works. That's all you need to know for now. Now we have linear actuators, which are very scary, and I don't like them, but they're good to know about. So basically, they are linear movement devices, which are useful in many applications, and there are a couple varieties. So they move in and out, they move forward and back. Motors can do a lot of these things, and you don't have to worry about pneumatic cylinders or compression tanks like that. But it is useful to have a knowledge in pneumatics. Basically, pneumatics. This is like a little cylinder here. This cylinder fills up with compressed air, and then there's this thing's a piston, right? It goes all the way down here, and then has a ring on the back, like a little plate type thing. So when this fills up with air, starting here, it pushes this whole thing out, and it literally just shoots in and out. It's pretty much on or off, right? There's no modulation there. But you can use it to do many interesting things, like deploy an intake or deploy a climber. Really, when you see pneumatic actuators, they're mostly just deploying stuff in low stress situations. But they are good things to know how to use. They can also be useful, like in a small scale, for like moving things around if you don't want to have to worry about motors and the accompanying infrastructure. Like just having like a small range of motion, like tensioning, or like squeezing something. You can use pneumatics for that. And you have linear servos and solenoids, which are different actually, but um, they're like electronic pneumatic actuators, but they're not pneumatic. They just move in and out with a smaller range of motion. FRC actually limits the size you can make a solenoid actuator, so they're not really used much. But yeah, basically they're electronically controlled linear motion generators. So they can be simpler, right? They require a lot of current to operate, and yeah, they just move in and out. Pretty cool. All right, now we get to moving parts, right, which translate the movement from the actuators that you just saw into a usable force, right? So first we have rotary parts, which spin. That's in the name, but yeah, they spin. So hex is really just what you use to transfer rotational energy across distance. So it's a shaft that spins, right? Your motor's on one end, and then whatever you're spinning is on the other end. And because it's hexagonal, if you put it in a hex-shaped hole, the thing it's on won't move, or it won't move. Hopefully the thing it's on won't move, because then you can spin the thing it's on if this is spinning, if it's not moving relative to this. So yeah, and then bearings allow hex to spin freely so that it supports it in all directions from loads that it may encounter. but it also allows it to spin freely while it's receiving these loads. Then you have hex hubs, which basically, like, you can just make hex shaped holes, but hex hubs are like a common off the shelf solution. So you can just, stick the shaft through there, bolt this to something, and then when you spin the shaft, the whole thing, this thing will move, and then whatever it's bolted to will move as well. So yeah, bolts to the parts that need rotation, which is usually like 2x1 or aluminum gears or sprockets or wheels, something like that, which wheels are the next thing we're going to get to. So they used to translate, basically wheels translate rotary movement into a usable force. So rotary parts translate motor movement across distance, or they help to do that, and they translate it between stuff. And then wheels sort of translate that to your game piece usually, or the ground, right? If you want to push forward, you apply energy to the ground through a wheel. So wheels are usually used to translate rotary movement into a usable force, and there's a bunch of different types. Compliant wheels are squishy. Coulson wheels are not, although they're a little bit squishy, but they're very durable. Coulson wheels are awesome. Traction wheels are sticky, but not super sticky, but they are sticky, and they're good for dry bases. Pneumatic wheels are squishy and sticky, like tires, good for dry bases on like all-terrain surfaces. Omnidirectional wheels are not squishy, not sticky. In fact, they're the opposite of both. They're pretty firm and they can move in both directions. So if you have these, they can be well used on drive bases to help turning, and they can also be used in like something like an H drive to get like omnidirectional drive. So you can drive forward, you can also drive side to side, which you can't do with just a regular 6x6 like tank drive or like a regular tank drive base with traction wheels. If you have like a tank drive base with one perpendicular omni wheel in the middle, then you can drive forward and back and then strafe side to side. You have a mechanism wheel, which also facilitates strafing in a drive base, but they can also be used. Basically, what a mechanism wheel does is when you spin it and it touches something, it moves that thing this way, moves it perpendicular to the axis, or it moves it parallel to the axis of spinning, actually, but like perpendicular to the direction in which it's spinning, perpendicular to the surface speed. So yeah, basically all different wheels with all different applications. Like compliant wheels are usually used for grabbing stuff like intakes. You don't really want to use these on a drive base because they're bad for a drive base and you'd be bouncy. You can get different levels of compliance, right? You can get harder compliant wheels or softer ones. The green ones are the softest. The black ones are the hardest, I believe. And then, right, so they're good for intakes. They're good when you want to interact with game pieces and really grip on them because they can squish down and apply a lot more force and squish that way. Coulson wheels are durable, so they can be used in pretty much anything, actually. Traction wheels can be used on drive bases. Pneumatic wheels, drive bases. Omni wheels, drive bases, maybe intakes too. Mechanism wheels, drive bases, maybe intakes too. Also, forgive my pronunciation of the word. Nobody knows if it's mechanism or mecanum. Really, nobody knows. So just pick one, honestly, and stick with it. Don't be one of those people who's like milk or milk, or they just say both. Yeah, or like GIF or GIF. I don't even know. All right. So rotation transfer, devices that are used to carry a motor's rotation to other locations. And that's what we said before, like hex carries it along the axis of rotation. Well, rotation transfer elements carry it perpendicular to the axis of rotation. So this is connected to a shaft, and then, or we'll go with the sprocket. This sprocket's connected to a shaft, and then a chain goes around the sprocket and connects to another sprocket that's connected to another shaft. So when this shaft spins, it spins this shaft as well, right? Belts are the rubber version of chains and sprockets, so belts and pulleys. And then you have gears, which actually like mesh directly with each other. So when this one spins in this direction, this one spins in the opposite direction, which can be used either to reverse motion or to get like some sort of a reduction. Because if you have a bigger gear going in here, and that goes to a smaller gear, for the same number of rotations per minute, or for the same surface velocity rather, it's going to have a different number of rotations per minute, different number of RPMs, which is going to give you a reduction. So if this one's spinning slowly, a smaller one, or if you're spinning this with a smaller one rather, this one's going to move slower than the smaller one. So yeah. And then you can also do reductions of the same nature with belts and sprockets. using different sized pulleys and sprockets, or belts and chains using different sized pulleys and sprockets. So yeah, different stats here. Really, all you need to know is that chains and sprockets, chains you can sort of adjust the length of, they're pretty customizable, but they're a little bit heavier. Belts are, you have to buy them common off the shelf, you can't really make them yourself. Pulleys you can sort of make yourself if you want, if you have a 3D printer. And belts and pulleys are more efficient and smoother, but they're also lighter, but they're also a little bit harder to integrate into designs. Gears have a whole lot of applications, so just keep those in mind. All right, now we have hardware, which holds everything together, right? Hardware is used to fasten parts together, and just ignore that last part. All right, so first things first, mounting hardware, right? And this is sort of lumps in with all the rest of the hardware. Hardware holds stuff together. So these holes here on this gusset, which is just it's just a word for a flat piece of metal with holes in it. This word here on this gusset, these holes correspond to holes on VersaFrame, right? So you would put these and then have two pieces of VersaFrame there, and then your bolts would go through these holes, through the holes in the VersaFrame, and then through the hole on a gusset on another side, and then you would have a nut that clamps down onto that bolt and holds everything together. Brackets work the same way, just on angles, and they don't have to be 90-degree angles like pictured here. They can be any kind of angle you want, any kind of angle that matches your joint. So yeah. Now we have fasteners, right? So what I just talked about, bolts are, it's just a piece of metal with threading, and you have a nut which has threading on the inside, so you can thread that nut down onto the bolt, and then it'll move back and forth, right, when you spin it. So when you spin it, when you apply a rotary force, it'll translate down, and it'll tighten. It'll squeeze whatever's in the middle here. And then you have rivets, which sort of like if you pull on this, it bows out here. So they're single-use items, but they only need to go in one hole. Whereas bolts and nuts, you have to access both sides for it to work. Rivets, you only need to access one, but to get it out of the hole that it's in, you need to drill straight through it. And then you have zip ties, which are like literally the best thing anyone's ever invented ever. And yeah, they're pretty awesome because, well, I mean, that's just what electrical team thinks, but like, you can put them around stuff and then you can zip them and hold stuff. So that's sort of more of a joke, but like, they do have their applications, but they don't really have a place on here. So yeah, conclusions, right? Key concepts: designs are purpose-driven, but they're constrained by the available parts, materials, and construction techniques, which we didn't talk much about, but we will later, that you have available, right? So effective designs are built around usable materials and the techniques that you have to machine them. Many parts and materials are possible to use in the FRC, in the first robotics competition, but some are more effective than others. Like either that means cheaper or more expensive, or cheaper or stronger, right? Or lighter. There's many considerations. Or has more holes from when you buy it. A lot of considerations, but you'll start to become a little bit more familiar with all of these parts as we continue. So when designing, right, you want to consider which materials and hardware would be the most effective. And now what I said here, the word I threw around was machining techniques. Basically, that's how you turn the part that you buy into the part that's in your design. So making it the right length, cutting holes in the right places, stuff like that. And how you would do that, it's important to have a knowledge of mechanical manufacturing techniques when you're designing, because that's what you design around. So we'll just go over an overview. How would you make this, right, this piece of VersaFrame? Let's say it ships 20 inches long, and you want to make it 8 inches long and drill a hole through it, right? So you're going to make a mark at 8 inches from the edge, and then you're going to use that to cut it, either using a radial arm saw or a bandsaw or a portaband or a jigsaw or a table saw maybe, or a chop saw, something like that. Whatever tool you have available in order to cut it to the right length. And then you're going to use a drill bit on a drill press, hopefully, so you get a right angle, down through in order to make your hole, right? You want to make a 1-inch hole or 1 1/4 inch, 1 1/8 inch hole for a bearing, for a hex bearing. So you get your pilot hole, right? You drill a hole through on your mark, and then you drill through with a step bit, and that makes the hole bigger. And then once that hole is the right size, you can use that thing for the intended purpose, right? It now matches the CAD. So that's sort of the process. That's sort of the workflow mechanical goes through. But it's just good to keep that in mind when you're designing these things. All right, so concluding, and now we're going to do a bit of an activity. We're going to examine the 2020 Robot CAD, which shouldn't take more than like 5 minutes. But we're going to go to Onshape and we're going to examine the CAD, trying to keep this grounded in reality to show how each type of part is used on the robot. So how would each part be machined into what's present in the CAD design? So I'm going to go ahead and switch to I'm going to go ahead and navigate to the CAD real quick. Right, we'll go up to here, open a new tab, and we'll go ahead and go find our robot, go to off-season, and then presented practice documents, and we'll check out our 2020 competition robot, right? So we've got 4 main categories of parts here. We've got raw materials, we've got moving parts, we've got actuators, which move moving parts, and we've got hardware, which holds everything together, basically. And Onshape's taking a second to load because my internet's a little bit slow, but now we've got it. We've got a loaded mechanism here. So yeah, we've got our robot from last year here. This was imported from Autodesk Inventor, so we had to do a little bit of work to get it to work well in Onshape. Just because step imports don't retain their assembly constraints. So basically when you move this, instead of, this whole thing rotating like it's supposed to, it's going to wind up actually just like you're going to wind up yanking this off. So that's no good. But yeah, so let's look for the type of parts. First, raw materials. Can you find metal on the robot? I feel like Dora asking that question, but it's kind of applicable, right? So yeah, here's an example of where 2x1 stock is used, and this is stock, not VersaFrame. This pocketing is done by us because it's pretty cool. We're gamers like that. And then you have this also is a raw material, right? And you can see that these make up, seeing a common thread where these make up the main structural members. Here's a sheet metal part, right? And this is custom. It's a sheet metal gusset actually, so but it's custom manufactured. And then you have more metal, right? Just being used to sort of hold everything together and give everything, make structural members. Here you have an A-frame, and that supports the climber. All right, next let's look for actuators, and that's going to look like motors and pneumatics. We don't actually have pneumatics on this robot, so it's just going to be motors. And I'll tell you what we have. 7 on the robot. Yeah, we have 7 motors on the robot. So we have 4 driving the drive base, right? 4 of these. And these go to a gearbox, which is a moving part that we will talk about. But yeah, these go to a gearbox. And they spin gears, which output to this wheel, which then connects by chains and sprockets to the other 2 wheels. And then you can see we have the same sort of setup on the other side, right? So we can control each side independently and with the same amount of strength. Then you can see we have another motor here, and this actually actuates our elevator so that our elevator can go up and down. All right, lift this up, lift up, and that motor is what's responsible. Right? So this will come up, and then this motor will spin the other way, and it'll come down. And I'm not going to get into how that specifically works. Actually, I will. Basically, you have a chain here, right? Chains in CAD don't really mix, so we just imply them, right? We heavily imply them, leave all the infrastructure in place, and maybe do like mock-ups of them. Yeah, here you have a sprocket down here. There's actually a planetary gearbox connected to the motor here, right? You can see you have stages there for your gearbox. Your motor connects in here. You've got a sprocket connects to a chain, which connects up here, but up here doesn't really matter. That's just a coasting thing. What really matters is that your chain is bolted to your moving stage. So as your motor spins, you can see here we have that relation there. As your motor spins, it spins the chain, which is connected to this moving stage, which then moves up as the chain, or as that section of the chain moves up, as that little joint of the chain moves up, right? So that's basically how, that's another example of a motor. Another example of a motor is in rotary articulation, right? So this motor down here spins this rotary arm, which basically it's just connected by these gears. But when you spin this, when you spin this motor, this arm can move up and down. And then you've got another motor here that spins these wheels. Right? It spins this wheel here. And this wheel basically acts to intake balls off the ground, so as well as outtake them. So your arm comes down like this, this wheel spins, and the balls get kind of, pulled up into there, and this whole thing moves up because of this motor down here, right? This motor right here, and these spin in the opposite direction, and the balls come back out. And they're all stored, 5 of them are stored up in this hopper here. All right, yeah, so reset that back to normal. And we'll leave it like that. Okay, so yeah, basically like that's sort of a little bit more just trying to keep it grounded in reality, trying to keep it applicable, trying to keep it practical. All right, so that's, in conclusion, we talked about different parts, right? We've got 4 different types of parts: raw materials, actuators, moving parts, and hardware. Each one has its own purpose, right? And you pretty much use them all the time. So next time we'll start to learn a little bit more like specific manufacturers. Actually, next time we'll be learning applicable assemblies, but after that we'll start to explore in CAD, like using these parts to actually make assemblies like I just showed you. All right, so yeah, that's pretty much going to be it. If you have any questions, I would appreciate if you went ahead and asked them, because I'll try my best to answer. And yeah, thank you so much for watching, and I'll see you all in the next one.